attached to this one is white plastic pipe. Can you see that one? Okay. So inside this plastic pipe there is a simply a wire. Okay, what we call as the vertical electric field antenna. Okay, here. So you know that electromagnetic waves have got electric field vector, magnetic field vector. The magnetic field vector can be sensed by the loop antennas there, and then the electric field vector can be measured by a simple wire. So inside this there is only a simple wire. Okay, here, and that is called as the vertical electric field antenna, which measures the EZ component of the electric field vector of the electromagnetic waves. And then at the base of this one you will see a steel little pipe. Okay, at the base of this steel pipe you see a steel box. Okay, can you see that one? The plastic pipe, then this galvanized steel pipe, and base there is a little box. That is a pre-amplifier. Okay, here it is amplifying the signals which are sensed by this vertical electric field antenna. Okay, and this antenna is so powerful. Okay, system is so powerful that it can measure the ELF and VLF signals produced by the strong lightning discharges in 5,000 kilometer radius of this station. It can also measure those strong VLF signals coming from different navigational satellites. Okay, but this is primarily used to detect the lightning discharges. Okay, if you guys go, and you guys, all of you have to go, write the worldwide lightning location system, WWLLN, worldwide lightning location system. Okay, so this WWLLN, to detect the lightnings, first of all regionally, was a PhD project of a student in Otago University. He used 3 stations and then developed this lightning network for New Zealand, and later then they extended it to the Australian region. So 3 more stations in Australia. And then in 2003 they approached us. They said that we will provide you the free hardware if you can record this data, set up this one here, and we will share with you the free lightning data. Okay, since then we established this one in 2003, and we are a part of this network. The network started with 3 stations, then 6 stations, 7th one were asked to join, and now it has got 50 stations globally detecting the worldwide lightning locations. Okay, you guys will go to the internet and we look at the real time with a 10 minutes gap. Okay, how the lightnings are happening in different parts of the world. Okay, so it is a part of worldwide lightning location network, and we started in 2003. It is maintained by Neil. Neil, can you raise the hand? Everyone knows you. And since then, he is the one who is looking after the technical part of this. Okay, the technical part of GNSS, the technical part of the exponential. Okay. Yeah. Now, if you come this side here, you guys will see there the 2 GPS antennas again in this balcony. Okay, and you will see those 2 GPS antennas there. Okay, those 2 antennas are coupled with this woolen system, worldwide lightning location system, to exactly give us the timings of the lightnings happening. Okay, so those little antennas on the roof, you can see little antennas, they are used to find the exact time of their lightning. They are coupled with this lightning system. Okay, here. All right, now then we have got a part of this one. You will see there. Okay, so if you see from here, you will see another plastic pipe. If you see from here, you will see 2 GNSS and GPS antennas and another plastic pipe. Inside this there is a similar vertical electric field antenna. Okay, of which we are recording the different signals coming from different navigational VLF transmitters. It is measuring here. All right. Now let's look at those 2 GPS antennas. One of them is working, one of them is right now off because we use one at a time. And you know that the ionosphere has got the ionization starting from 70 or 90 kilometers, goes up to 500 kilometers. It is used for the satellite communication as well as for the TV communication here, and it is known by its electron density. So with the help of this antenna, we are measuring the electron density variation over this station, okay, here. And then when the GPS signal passes through the ionosphere, in the path the ionosphere is not very quiet, changes from day to night, and then changes under the natural hazard conditions. So small structures of the different electron densities are formed. When signal passes those structures, it gets faded up, okay. It has got the fluctuations like this. Signal is coming from here, passes that irregular structure and goes for the fading, okay, here. That is called scintillation. We will do in the later part of the course. So with the help of this, we are measuring that fading or the scintillation over the L1 band signal, okay. And L1 and L2 bands are used to measure the electron density, okay. So we can see that if there is a fluctuation in electron density, there is a fluctuation in signal, and at times this fluctuation can be so strong that the signal can go below the noise level and that we don't see any signal, okay, here. This is where it happens when you are using a GPS. All of a sudden GPS has gone down, okay. It has disappeared. Maybe apart from other technical issues, it can happen because of scintillations also. In the lab, we have got the computer system. For this system measuring the electric field, we have got the computer system for measuring the electron density and then the scintillations. We do not have a time right now, but sometimes I will take you to those lab and I will show you how these systems are recording the data, okay. We have another system here which Anishal has used for his master's thesis. It measures the electric field induced inside the ground because of the strong earthquakes, okay. So there is no time for that because the bus is about to come. We have to start 10 o'clock. But we also measure the potential generated inside the ground, okay. Anishal, would you like to explain for a minute about this? Okay, so what we have done here, we have got here 1, 2, 3 pits here. We have got here every pit inside the ground, half meter, so on. Okay. Over to you.
These 3 pits, and each of them are dug in northwest, central, and southeast over here. And all of those pits have 4 electrodes. 4 electrodes that are around 30 centimeters to around 50 centimeters apart, and they are way underneath the ground, around 1 to 1.5 meters underneath the ground. And they measure the potential difference between the plates, between the ground itself, and between other pits, plates from other pits. So if there is any type of earthquakes, it lends a small vibrations that disturbs the tolerating current that is flowing inside the, it's in global current that is flowing inside the earth that connects it to the ground as well. I think the professor mentioned it over there, right? So any type of earthquake creates a disturbance, and we are able to record that in that lab over there, right? It was installed in 2017, yes, 2017. And during that time, any type of earthquakes around 5,000 kilometers in radius from the station over here, we can actually detect it, and we can actually see whether it can be, let's say, different magnitudes and different radius. So depths of earthquake leads to different amplitudes in the signal. So if we can identify it, maybe the future prospect will be to predict the earthquakes itself.
So guys,
But that's still the future.
the systems are quite cost effective, not very expensive, but the rain is saying that we stop here. Okay, and we move to the bus, but you guys will, you understand what I said, okay? And Anishal is going, his thesis will be in the library very soon. You can see this earthquake system, but it's not a part of your field trip, okay?